We've established a process for how to identify local extremum when we're dealing with these multivariable functions. So let's take a look at an example. We want to find all local extrema for f of xy equals x squared plus y squared minus 10x minus 2y plus 36. So the first thing that we want to do here is find the first derivative of this function with respect to x and with respect to y. So the very first thing we want to do is find the derivative with respect to x. So f sub x is going to equal the derivative of x squared is 2x. Y squared we just treat as a constant, so that becomes 0. We get minus 10, 0, and 0 since there's no x term there. So we take that first derivative with respect to x and set it equal to 0. Adding 10 to both sides and then dividing by 2 is going to give us x equals 5 as one of our coordinates. Then we also need to find the first derivative with respect to y. First derivative with respect to y is going to be 2y minus 2. So setting that equal to 0 and solving for y is going to give us positive 1. So this means that our critical point to consider is the point 5, 1. Now this may end up being a local maximum, it could be a local minimum, it could be neither, so we have to run through the test to determine which this is. So we'll find our value for a, which is equal to our function differentiated with respect to x, differentiated with respect to x, and then evaluated at this point 5, 1. So we can find a by first finding the second derivative with respect to x. So we took the first derivative with respect to x, we got 2x minus 10. The second derivative then is going to be 2 minus 0. So all our variables are gone, we don't have to worry about evaluating this at the point 5, 1. We just get 2 there. We'll find our value for b, which is taking the first derivative with respect to x, second derivative with respect to y, and then if we have any variables left over, plugging in x equals 5, y equals 1. In this case, when we take the derivative of 2x minus 10 with respect to y, we get 0, since we treat this x as a constant. So the derivative of a constant, derivative of a constant, just gives us 0. And let me actually just put this in as an intermediate step here. So f of xy equals 0. And then we need to find our value for c, which is the second derivative, both differentiated with respect to y, evaluated at x equals 5, y equals 1. So we take our first derivative with respect to y and differentiate with respect to y again, is going to give us 2. So we have our values for a, b, and c, which means now we can find ac minus b squared. Check to see is that positive, negative, equal to 0. So we take a, which is 2, times c, which is 2, and subtract 0 squared is going to give us 4. So that's a positive value. So we compare our value for a to 0, and in this case our value for a was 2. So our expression ac minus b squared is greater than 0. A equals 2 is greater than 0. So if we go back to what we mapped out for that second derivative test, this tells us that this is a local minimum. So f has a local minimum at f of 5, 1. And then if we plugged 5 and 1 back into the original expression, we would get a result of 10. So our function value at 5, 1 is going to be a function value of 10. And again, in this case, we found this critical point 5, 1, ended up being irrelevant because we didn't have to, or those values weren't terribly important because our second derivatives in each case just came out to be whole numbers. But in other cases, our second derivative is still going to be some expression in terms of either x, y, or both. So we will have to make some substitutions to evaluate there. But in this case, a relatively simple process or a relatively simple problem to introduce how we apply the second derivative test.